Hi, welcome to Lecture 1 of EEE 107. EEE 107 is Introduction to Communication Systems. In this first lecture, I will introduce to you the concept of communication. How does communication work? And how do we create communication? How do we transfer data from one point to another? How do we model it? How do we think about communication in the first place? So what is communication? So according to Hyken, which is the author of the reference textbook, in the most fundamental sense, communication involves implicitly transmission of information from one point to another. So the key word here is transmission of information. So how do we define information? So the information is not really easily defined. A definition of information was a mathematical definition of information was formulated by Shannon in the, I think it was the late 1950s or so, and revolutionized information theory. But how we think of information and how Shannon mathematically defines information is quite different. Well, information could be of the form of words or maybe a description about the president, let's say. Let's say the president is conservative. That's information. That could be information to you. How did you know? Well, you read about it in an article, an online article. Maybe you clicked the link from Facebook. It was not clickbait. It was from a reputable news source. Okay? And that is already information getting to you. That information passed through electronic means to get to you. For example, it's in your Facebook page or timeline. You saw it in your news feed and so on and so forth. And that the process of how that information went through, that's a communication system. It went through a communication system. So the information was encoded electronically, was published online, an article was uploaded somewhere in the internet, and then you access that article through the internet, which, well, the internet is a series of connections of cables and so on and so forth, and computers, routers, so on and so forth. That's an example of your communication system. It facilitated the transfer of that specific information to you. Okay? So communication is actually observed every day in our daily lives as we go about and talk to people, do transactions, order food over the counter, or buy your groceries. Communication can actually be found in our everyday lives. It's actually how we live also. As for example, you have your human here. It's saying something. The human is saying something, and the human produces sound waves. The sound waves propagate through the air, and we hear it through our ears, and any sound wave will be converted to electrical signals, which will be processed by the brain. So this is an example of a human communication system. Let's look at how it works. Information is generated in human brain. Okay, let's say this is the information. Very abstract, right? Just picture image of a cat with a heart. And the human translates that to words. Of course, how will you communicate? You don't communicate using pictures, right? You communicate using words. So the information generated by the human brain will be converted to words, and the words will be converted to sound. But not all of our speech boxes, our mouths, are perfect. The way we say I love you could be I love you. Something like that, right? Maybe you were nervous, you stuttered, and you didn't really want to say I love you. Maybe it's too soon in a relationship, I don't know. But you stuttered, and instead of saying I love you to the fullest, say I love you. So it's very fast. Maybe it could be very fast. It just came out that way. So that's already the sound that you made. And external noise could also corrupt whatever you said. So what the ear hears is I love you. Something like that, like here. And it will be converted back. So the ear can actually maybe correct it, and you can still get the same message across. Right? So the information generated here can now be found at the other side, and we now have achieved communication. Okay. So the breakdown of the communication process is quite simply, in the simplest form, 5 stages. You have your information source, and the information will be shaped by the transmitter. Transmitter shapes it in a suitable form so that it can pass through the channel. And over the channel, your receiver is connected there. It listens to the channel, and it processes the signal back, and it gets to your destination. So this is how the communication system works. This is how we view the communication system in a general sense. So to communicate, you need to have an information source. This information source will go through a transmitter, which converts the information to a suitable form. So you can transmit it physically through a channel. A channel is inevitable. The channel is always there. And the receiver listens in the channel and converts whatever it picks up back and transmits it or delivers it to the destination. Okay, so this is your communication process. So let's view the human communication as such. We have a source, right? That's the brain. It generates information. This information will be converted into a suitable form. First, when we think about something, it's very abstract. When you think about something, it's in an abstract form. It's not tangible. But when we try to communicate what we think, we convert it to words, because that's how we communicate. It could be any language. It could be this one, English. It could be Tagalog. It could be Ilocano. It could be Ibanag. It could be Japanese, Nihongo. It could be Mandarin, whatever. Depends on the culture also. But for the sake of instruction, yeah, let's say it's English, right? So you have information in your brain, you have your thoughts, you want to communicate your thoughts, then you convert that into words. And once you have the words laid out in your head, then you convert it to sound. Because a corresponding word has a corresponding sound. And this sound is the physical manifestation that will be transmitted from your mouth towards the channel. So it will be propagated towards the channel. The channel is imperfect. The channel could be noisy. The channel could offer some distortion. And whatever sound was emitted from the mouth will be heard by the ear. So it will be picked up by the ear, okay? And then the ear will correct whatever distortion that would happen if it's correctable, right? If it's intelligible. If you murmur some words, maybe the ear won't hear it and you get misunderstood. So your transmitter should be powerful enough to be able to communicate, right? And then it will be transferred to the destination. Information will be decoded there, and you have a successful communication as humans. And you can look at it in very different ways. Maybe let's say the channel is wireless. Use your phones. So you're speaking through a phone, okay? This phone emits signals. It will be received through another phone that is being used by the other user. So it picks up that signal, okay? And that will be converted to sound and it will be heard by the secondary user. Okay, so the channel can take on many forms, and you need to shape the signal. As communications engineers, you have to shape the signal such that it will go through the channel safely, so you can achieve successful communication. Okay, so let's look at the process then. So what we can control as communications engineers is the transmitter, or what we call the modulator, and the receiver, what we call the demodulator. So what is modulation? The modulation is the process of transforming your message, an abstract concept, right, and your thoughts, your message, into a suitable form, suitable physical form. And the physical form that we think should be in waves, right? Well, not necessarily in waves. That's just for wireless communications. You can think of it as a physical signal, like goes through a wire. It could be a current through a wire, or it could be light passing through a fiber optic cable. So the transmitter shapes the message in such a way Okay, so it could have a physical form to go through the channel. So there are two parts for modulation: the representation of information and the physical manifestation. Okay? The modulation just reverses the process. So of course, your information source and your destination could be the same, right? So just person to person, let's say. We use sound by default to communicate. But if you want to communicate over long distances, you have to convert that sound to an electromagnetic wave. And from an electromagnetic wave, convert it back to sound, right? So the modulation process converts your sound wave to electromagnetic wave, but the demodulation does the reverse from the electromagnetic wave to the sound wave. This is your modulation and demodulation process. And this is what we design. Oops, sorry. Okay. This is what we design, okay, as communications engineers. There you go. Okay. So what is then information? So the information, as I've said earlier, is an abstract concept, but we can represent information in different forms. Right? And this is part of your modulation process. For example, the letter A can be represented in different forms. Could be spoken, right? Could be written, capital or small a. Could be in sign language. So if you can't communicate by sound, if you have a hearing defect, you can use hand signs for you to communicate. Could be in Morse code. If you can't write it or if you can't speak, maybe you can use taps or Morse code or whatnot. You can use touch, Morse code. Braille code also, for if you can't read, can represent A by the sense of touch. Or in terms of our computers, you can represent A as the number 65 or the binary code 0101 000001. Okay, and this is a part of your modulation process. It's modulation step 1, sorry. It's modulation step 1, you represent your information. Right? And how we represent information, well, there you go. So it's kind of like when if you are use a certain form of information, right? Use a certain form of information when you are restricted by the channel, right? So if you're restricted, So if you're restricted by the channel, well, let's say you can't speak. If you can't speak, then you use sign language or Morse code. If you can't write, then you use Braille code or maybe even Morse code. You use your blinking so you can transmit a message. And I actually saw a clip about a soldier that is blinking, irregularly. It's actually transmitting Morse code. Or you can use light. You turn your light on and off so you can achieve Morse code. So that's an example of communication already. And you're communicating by not just speaking, right? You can communicate in many different ways. Okay. So the effects of channel. So the channel will always be there. The channel will try to impede your communication. The channel is not your friend, basically. And in the channel, you have an attenuation, the reduction of signal strength as you go further away from the signal source. Noise, so your random and unpredictable signals, not just electrical. It could be background noise when you're talking to each other. It could be from the noise from the environment, could be the noise from the wind, and so on and so forth. But when we talk about electronic communication systems, we're talking about the random motion of electrons because of temperature. So the higher the temperature, the larger the randomness, quote unquote, of these electrons. And it's always present in communication systems. Distortion is the alteration of the shape of waveforms due to your imperfect response of your system. Okay? And interference, it could be a malicious intent or intended impedance of communication. So it Could be an external or maybe an interpreter. It doesn't want you to communicate successfully. Okay, so it's contamination by signals from other transmitters and signal jammers. Okay. So how do we measure the quality of transmission? So the goal is at the receiver is to produce an acceptable replica of the source message. Okay? There are two types. You have an analog and a digital signal. So for analog signals, we measure what we call their fidelity. We want the recovered signal to be approximately the same as the transmitted signal. Okay? For the digital signals, the performance is measured, it has more flexibility actually. Could be in the data rate, how fast can we transmit the message, how many bits can we transmit in a second, and it could be measured in terms of how many bits are in error when you transmit a signal. So for example, you have this illustration right here. The transmitted bits would be this, but when the receiver tries to decode it, there are errors, as you see here. Okay. For analog signals, it's maybe you transmitted a sine wave, but when it was received by the receiver, there was noise, as you can see here. You wanted to transmit a sine wave, tough luck, there is noise. Right? So when you try to hear that sine wave, it becomes noisy. Maybe you won't be able to hear it at all. Right? So what are the metrics for quality of transmission? So, before we go there, let's look at the transmission modes. There could be a one-way communication only. This is for an example would be radio and TV, FM radio and TV. Okay, so you're broadcasting over receivers, right? So that you're broadcasting content to the receiver. It could be two-way communication. There's a downlink from the base station and uplink towards the base station. This is for your mobile handsets, a full duplex communication. And there could also be a half duplex. For example, would be amateur radio. I suggest you read up on this. It's an interesting hobby actually, amateur radio. You can only transmit and receive one at a time. So if you're transmitting, then you cannot receive. Or if you're receiving, you cannot transmit. Okay, so these are example of transmission modes. And when you're designing your communication system, there will be limitations. Could be technological limitations, your hardware ability, economic factors, government regulation. This is actually the most painful one. Because, for example, when you try to transmit wirelessly, okay, the frequency that you want to use could be regulated and you won't be able to use it. Luckily, for an example would be your TV. TV frequency would be 470 megahertz towards 790 megahertz. Okay, and if you transmit anything other than TV signals in that, and that's already illegal. And if you're not registered in the database of our local telecommunications regulator, that's also an illegal transmission. Okay, or we call it colorum. Okay, economic factors. Well, generally, communication systems are very expensive. So when you think about the infrastructure that you need to be able to have a high fidelity communication system, well, this costs a lot, okay? And also the hardware ability. You're limited by how fast or how much data can your device handle, right? So when you talk about bitrate, let's say your plan is 100 megabits per second, is actually very low. So your DSL plan is 100 megabits per second. If your computer cannot handle that speed, maybe you feel like it's just 1 megabit per second. Okay? Maybe it's because of your computer. If you're using an old model, that's why it can only go up to 1 megabit per second. There are also physical limitations. The physical limitations determine what can and what cannot be accomplished. Example would be bandwidth. If the bandwidth determines the amount of information the system can transmit, and you have also the noise. The noise, again, is always present in communication systems. It's natural and unavoidable, and it's actually the mortal enemy of your communication engineers, right? So you have to work around with what you have. Okay. And the signal bandwidth, if your signals, can be classified as wideband or narrowband signals. Right? And it depends on what we call the coherence bandwidth of your channel. So if you let a signal pass through a channel that has a non-flat response, something like this, the response of the channel varies with frequency, of course. But let's say if you have the channel varies from here to here in its frequency response, you will define what we call a coherence bandwidth. So the coherence bandwidth is the bandwidth at which your channel is approximately flat. Okay? So the wideband signal has a bandwidth greater than the coherence bandwidth, and if it's less, then we call it a narrowband signal. Okay? So the noise refers to the unwanted random signals that tend to disturb the quality of the received signal. So the noise sources could be internal within the system or external outside the system. Internal noise could be caused by the temperature. Because a higher temperature, your electrons tend to go in a more random pattern in your wire, creating a fluctuation of voltage and current within the wire, creating noise. Okay? External would be atmospheric noise, lightning discharges from thunderstorm, and we use the signal to noise ratio to quantify the degradation in signal quality. Okay? So a question then, something for you to think about: can signal amplification at the receiver improve SNR? Example: compute the SNR if the signal power is 10 watts and the noise power is 100 milliwatts. So basically, it's just a ratio. So the signal divided by noise, you get your SNR. That's 10 watts divided by 100 milliwatts. And that's the result that you see right here. The SNR is 100. Okay. So finally, a limitation on the data rate is imposed because of noise. So that is proven actually by Shannon. And this is the formula. The capacity of a channel depends on the bandwidth of the channel and the signal to noise ratio. Okay? So basically, the implication of this theorem is theoretically we can transmit at infinite data rate in a noiseless environment with 0 bit error probability. And this theorem actually gives an upper bound, but as of now, I believe there are no systems that has been able to achieve this upper bound capacity of any channel. Okay, so for example, so if the signal power and noise power in a certain communications link are equal, what would be the bandwidth, what would allow a channel capacity of 56 kilobits per second? So you just use the formula here and then work back. Your SNR is equal to 1 since the noise and signal power are equal. So substitute that here, and knowing that the capacity is 56K, okay, you can now solve for the bandwidth, which is equal to 56 kilohertz. Right? So just an example of what I saw. I actually hiked at Mount Gulugud Baboy in Batangas before Christmas. I think this was taken December 19, 2019. Right? And I saw a communication system or just some series of antennas atop the mountain. I was wondering what it was for. My best guess would be it is a relay trying to communicate over the mountain. So Mount Gulugud Baboy stands at 400 meters, okay? And there are other mountains near it. And if you want to communicate from here to here, it needs to go over the mountain, but electromagnetic wave cannot do that. So what the communications engineer did is it set up a relay. Okay? So this is the relay that's atop a mountain. This is, let me just delete that. So this antenna will receive a signal and then redirect it towards the other side of the mountain. Okay? So that's how communication over the Mount Gulugud Baboy mountain, the mountain, not Gulugud Baboy. That's how the communication works over that mountain. Okay? So that's the end of the first lecture. If you have any questions or comments or violent reactions, I'm kidding, or reactions, just post a comment in the comment section below.